Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back for another session, and this time we are talking about forces. Okay, so this is Unit 2, Lesson 1. We're talking about forces, and in this lesson we're going to describe what forces are, and we're also going to find out how forces affect motion. Okay, so let's have a go. So what are forces? How are they described? I'm going to write a quick summary right now, and then I'm going to explain as we go along, and inshallah it'll make it easier for you guys to understand. So let's have a look. What are forces? Forces are simply a push or a pull, and you'll come to understand what this means in just a minute. And how do forces affect motion? So it turns out forces can affect motion by either changing the speed or the direction of an object, and they can also change the shape of an object, but we're talking about motion here, so they can change the speed or the direction, or as somebody has said in class, basically the velocity. If you change the speed or the direction, remember velocity is basically speed and direction. So there we go. And as always, what I'm going to do is I'm going to read through this. We're going to answer the questions, and I'm going to explain anything that needs to be explained. So let's have a look. Forces to change. Misconception. We have a misconception here, which means something that students think is true, but is not necessarily true. Any object that is set in motion will slow down on its own. That's interesting. Any object that is set in motion will slow down on its own. The fact is, a force is needed to change an object's state of motion. Yes, absolutely. So a soccer ball sits at rest. You come along and you kick it, sending it flying it across the field. It eventually slows down to a stop. You applied a force to make it start moving, and then it stopped all on its own, right? Well, not exactly. Forces cause all change in motion. Just as you applied a force for the ball to start speeding up from rest, the ground applied a force to slow it down, and this force is called friction. And not only the ground, but also air resistance. So when you are pushing a ball here on earth, say on the ground, you give it a wee kick, what happens is that ball will not keep going forever. We all know that. So if you're on the playground, if you're on the field, and you give that ball a wee push, a wee kick, what's going to happen is it's going to travel for a wee while, and then it's going to stop. Why is it going to stop? Well, it took a force for it to start moving, and that's called a push force, okay? But then what's going to happen is it's going to face air resistance, and it's going to face ground resistance, which is another name for friction. So what's going to happen is, as the friction force increases, it's going to slow down, and eventually it's going to stop. So that's basically a quick summary of what we're talking about. Let's look at some of the questions here. Give an example of a force that you apply to slow something down. I can think of two examples. So basically, air resistance is an easy one. That's used when a parachute is falling down to the ground. Obviously, as the surface area is quite large, the air resistance, the air gets trapped in the parachute itself, and the air resistance slows the parachute down. Another example of a force that slows things down is friction, obviously. All right, and that's used when braking. If you have a bicycle, or if you drive a car, obviously when you brake, you increase the resistance between the tires and the road, which causes you to slow down. So that's another type of force as well. Or simply speaking, if you're catching a ball, right? Like if you catch a ball, that's slowing it down as well. Where might it be possible to kick a soccer ball and have it never slow down? Okay, I want you to think about that one for a second. Where might it be possible to throw a ball and never have it slow down? Well, the only way that is possible is in a place with no air resistance and no friction whatsoever. Now, where is a place with no air resistance? Well, no air resistance means no air. Well, I think most of you have figured it out. It's outer space, isn't it? So in outer space, we don't have air, and therefore we don't have air resistance, and that ball will continue moving forever. And that's exactly what's happening with asteroids, okay? So they continue moving because there's simply no force to slow them down. Yeah, so let's carry on. Okay, we're going to watch this quick video, and it's going to give us a quick introduction in forces, and we'll continue with our lesson after. Let's have a look. Excuse me.
Types of forces. A pull or push acting on an object is called force. We can move objects, or change their shape by applying force. Force is applied by these children to kick the ball. Force is applied by these men to move things. Force may cause an object to stop or start moving.
Okay, so this is very important. Forces may cause objects to stop or start moving.
To change its position or direction of motion, to increase or decrease its speed, to change the shape of the object. The type of forces are gravity and friction. Gravity. What happens when we throw a ball up into the air? It first rises up, then seems to stop, and then falls to the ground. Do you know? Why does it fall down? Why doesn't it keep going upward? This is because of the force of gravity. The force that pulls objects downwards towards the center of the earth is called gravity. When you throw a ball up, you throw it with a lot of force, that is more than the force of gravity. So it rises. As the ball moves up, it loses this force, and then gravity pulls it down. Similarly, leaves and ripe fruits always fall down to the ground, due to the force of gravity. Friction. When a ruler is pushed across a table, it stops after moving a certain distance. It stops because of friction. The force that is present when two things are in contact with each other is called friction. Friction is the force that makes it difficult for one object to slide along the surface of another object. Friction resists the motion of the object on the surface. As a result, the object either slows down or stops moving. If there is no friction, anything that starts moving will never stop. If there is too much friction, nothing will move.
And this relates back to one of the first laws of motion, Newton's laws of motion, which is the law of inertia, that talks about how an object that is moving doesn't want to stop, and how an object that is not moving doesn't want to start moving. And we'll talk about that later on in physics, inshallah. Okay, let's have a look. Let's keep going.
Types of forces.
Oops, no, let's keep going. So, how are forces described? So, forces are described as either a push or a pull. When one object pushes or pulls another object, the first object exerts a force on on the second object. Okay. So, like velocity and acceleration, a force is described by its strength and by the direction in which it acts. Pushing to the left is a different force from pushing to the right. Okay. The direction of the strength and the strength of a force can be represented by an arrow. The arrow points in the direction of the force as shown in figure 1. So basically, forces are vectors, which means they have a direction, and the direction matters. So not only the size of the force, but also the direction of the force actually matters. The other thing I want you to take away from here is that forces are measured in newtons. Okay, so the standard international, or the international standard unit for forces is Newton, and that's after scientist Sir Isaac Newton. Right, over here we've got a photograph that shows a couple of men celebrating their win during the Beijing Olympics, and one of them is hugging the other, and they are pulling them, and of course pulling is a force, and as they are being pulled, the arrow is pointing this way, and then it's pointing this way, and they are getting pulled into the swimming pool. Okay, now I'm going to spend a minute now to talk about forces. Okay, so what I'm going to do is I'm going to draw a table, and on that table I'm going to draw an object, a vase, and that vase is sitting happily on the table. I'm going to draw a flower inside it. Now here's what's happening. That vase is not moving. It's not going up. It's not coming down. Of course it has a weight. Now that weight force pulling it down, okay, that's called the weight force. And then we have a force that's opposing the weight force that's pushing up. And that's called the normal force. So they're both forces. Now it turns out those forces are exactly the same. Why is that? Well, I'll tell you why. If, say for example, the vase weighs about 15 newtons, because remember, mass is one thing and then weight is something else. So mass is measured in kilograms, and it's the amount of matter an object has. So in this case, the vase has a mass of 1.5 kilograms, so the weight would be 15 newtons because it's 1.5 multiplied by 10 newtons, which is the acceleration towards gravity. Now, if the weight is 15 newtons down, that means the table has to withstand 15 newtons. What is the table carrying? What is the table withstanding? It's carrying or withstanding or pushing up with 15 newtons. So that's why we say it's pushing up with 15 newtons. And in fact, this is Newton's third law, which is for every action there is an equal and opposite reaction. Otherwise, what's going to happen? What's going to happen is if the table couldn't push back with 15 newtons up, it would break. It would break. So let's say, for example, an elephant is sitting on the table or standing on that table. If an elephant attempts to stand on that table and it's applying 5,000 newtons downwards, let's say, for example, it weighs about 500 kilograms and therefore the weight force down would be about 5,000 newtons. That table has to withstand 5,000 newtons. That's what it means. So it has to push up with 5,000 newtons. And if it's unable to do so, which is very likely, then it's going to break. Okay? So in order for this vase to stay the way it is, without moving, without either going up or down, the forces have to be exactly balanced. So it's 15 newtons down, 15 newtons up. Now what's going to happen if I apply a force this way, over here, and I apply a push force? Let's say I apply a push force of about 3 newtons. Now that push force is going to cause the vase to move to the left. Alright, why is that? Well, because I'm applying a push force, but there's nothing opposing it. Yeah, there's a bit of friction this way, and there's a bit of friction force, and there's a bit of air resistance, but it's not going to be big enough to stop me. Now, what if somebody comes along and they apply a force of 3 newtons in the opposite direction? Then this is a situation where all the forces are balanced. The forces on the horizontal plane are balanced, and the forces on the vertical plane are balanced. In this scenario, we call the forces in equilibrium. So this is what we call an equilibrium. Equilibrium. And that just means the forces are completely balanced. What does that actually mean in reality? It means there is no net force. Now that's a new term that many of you wouldn't have heard before. No net force just means that there's no overall force acting on the object, because all the forces cancel each other out. So the 3 from here cancels the 3 from here, because they are opposite and equal and opposite. And the 15 up cancels the 15 down, and therefore everything cancels out. The object is not going anywhere, it's going to stay still. So no net force. Okay, no net force. Very good. Now what if I change it slightly? What if I change the scenario and I say, for example, instead of pushing with 3 newtons, I say I've got a person over here, applying 3 newtons, right, with their hand. Now I come along and I'm going to push with 7 newtons over on this side. I'm going to push really hard, and I'm going to push with 7 newtons, right? So here's my hand, and I've got bigger hands because there's a child on the other side, and I'm on this side and I'm pushing with 7 newtons. What's the overall force now? Well, we can't say there's no net force anymore, because suddenly, yes, the downwards cancels with the upwards, but these two over here don't cancel out anymore. The 3 is not going to equal the 7. It's not going to be equal and opposite. So what's going to happen? We are going to have an overall force of 4 newtons to the left. So what's going to be the net force? 4 newtons to the left in this case. So the object is going to move. And the reason why it's going to move is because there is an overall force. There is an overall net force. Okay, let's keep going. So here's the scenario that we're talking about. We've got 2 dogs here. Both of them are pushing on this box. One is pushing with 16 newtons, the other one is pushing with 10 newtons. They are pushing in the same direction, so what's going to happen to their forces? Their combined forces are going to be just summed. You just add them together. So the net force acting on the box is going to be 16 newtons plus 10 newtons, and the overall answer, the net force, is going to be 26 newtons to the right. Remember to always include the arrow or say the direction, because forces are vectors. They have a size and a direction. What's going to happen in this instance over here in scenario B? The dogs are now pushing in opposite directions to each other. One of them is pushing to the right with 20 newtons, the other one is pushing to the left with 10 newtons. So what's happening here is 20 newtons minus 10 newtons, because obviously they're opposing each other. So the overall force is going to be 10 newtons to the right. Okay? And that's how we solve that one. Okay. Let's keep going. And how do forces affect motion? So by now you probably have an idea of how forces affect motion. The net force determines if and how an object will accelerate. So basically, if an object is moving and you apply a force from the back of the object towards the same direction it's going to increase its speed. And if the object is moving in one direction and you oppose a force in the opposite direction of where the object is moving, it's going to slow it down. I want you to imagine this scenario. If a ball is moving in that direction, but the wind is moving in the opposite direction to the ball, it's going to slow it down. What's going to be the net force? Well, it depends on the forces. Let's say the ball is moving and a force is applied and it's about 20 newtons, while the wind is applying a force of about 7 newtons. Then overall, the force acting on the ball is going to be 13 newtons to the left, and that's going to be the net force. Okay? Let's look at this scenario over here. We've got a question here that says, use the information in the text to determine the net force of these 2 force arrows. So we've got 3 newtons acting in one direction, and we've got 5 newtons, and they're both acting in the same direction, aren't they? So the overall force is going to be 8 newtons. But which way is it going to be facing? Well, it's going to be facing the same way. 8 newtons to the right. That's how we solve that one. Okay? So by now you would have figured out that if all the forces are balanced, if all the forces are in equilibrium, then there is no net force acting on the object. And if that's the case, then the object's not going anywhere. It's not in motion, it's not moving. But if there is an overall net force acting on the object from any direction, then the force is going to force the object to accelerate and move in that direction. Okay? Let's have a look at another scenario. So once again, we're dealing with 2 dogs. And the 2 dogs are pushing against the box. Now this time they're pushing with exactly the same force, equal and opposite. So what's going to happen now is the forces are in balance, and the net force is going to be 0 newtons. That's simply the way it's going to be. Why is that? Because they are equal and opposite, so they cancel each other out. Okay? Now, we've got a question here that we need to answer. Use what you know about net forces to describe the motion of the box. Assume that the box starts at rest. Well, I can tell you right now, the motion of the box is going to be not moving. Simple as that. It's going to be not moving. Why is it not going to be moving? Not moving. The reason why it's not moving is because the net force on it is 0, and therefore it will stay at rest. Net force is 0, and so it will stay at rest. Stay at rest. Very good. Let's go back. You pull on your dog's leash to the right with 12 Newton force. Your dog pulls to the left with 6 Newton force. Okay. Sketch this situation including labeled force arrows. Okay, sketch this situation. I'm going to try and sketch the situation, why not? Here we go. So that's the person pulling on the dog. And the dog's trying very hard to oppose the force of the person. Okay, that's the best I could come up with. So here we go. So we've got 12 newtons to the right, while the dog is pulling with 6 newtons to the left. Now obviously the person's still going to be able to push the dog, or is going to be able to pull the dog with an overall force of what? Of 6 newtons to the right. Now what I'm going to do here is I'm going to do something else. I'm going to draw what's called a free body diagram in physics. Now you're not required to know this, but for those of you that are interested, this is what the free body diagram looks like. And the overall force is going to be 6 newtons to the right. Okay, that is the overall force. So is the dog going to end up moving? Yes. And which direction are they going to be moving? They're going to be moving to the right with 6 newtons. So let's assess our understanding. You push on a desk with a force of 120 newtons to the right. Your friend pushes on the same desk with a force of 90 newtons to the left. What is the net force on the desk? Let's picture the scenario. You're pushing on the desk. Here's the desk. Okay, and I'm pushing with a force of 120 newtons to the right, 120 newtons to the right, while my friend is pushing with 90 newtons to the left. What's going to be the overall force? It's going to be 30 newtons. That's going to be the net force, 30 newtons to the right. 30 newtons to the right. Next, we have a prediction problem. Your friend increases her force on the desk by 30 newtons. She doesn't change the direction of her push. What happens to the net force on the desk? Will the desk accelerate? This time, the net force becomes 0. The net force becomes 0. Therefore, no motion. No motion, no acceleration, nothing like that. The desk will remain at rest. Okay, so now I know that changes in motion are caused by, what are they caused by? Non-zero net force. As long as there's a net force and it's not 0, that will cause an acceleration. Okay. And here we have a quick revision sheet to do together. Let's have a look. We should be able to do this. What I'd like you to do is I'd like you to pause the video. I'd like you to do it, and then you can play the video and see if you got the same answers as myself. So let's have a go. If you pull on one end of a skateboard with a force of 10 newtons, while your partner pulls on the other end with a force of 10 newtons, what do you think will happen to the skateboard? So by now, hopefully most of you know that nothing should happen, basically, because the forces are completely balanced. We've got 10 newtons on one side, 10 newtons on the other side, and this is Newton's third law. For every action, there's an equal opposite reaction. They cancel each other completely. There's no net force. It is completely 0 net force. So 0 net force, 0 net force, no movement, no motion. Question 2 says, If you pull on one end of the skateboard with a force of 3 newtons while your partner pulls on the other end with a force of 6 newtons, what do you think will happen to the skateboard? It will go 3 newtons towards the partner. 3 newtons towards the partner. Why is that? Well, I'm pulling with 6 newtons. Sorry, I'm pulling with 3 newtons. While they are pulling with 6 newtons, so my partner is applying more force, and overall it's going to be 3 newtons to the left. Question 3 says, make generalizations. Based on your observations, what can you say about an object at rest that's pulled in opposite directions by equal forces? We already know what's going to happen. Nothing's going to happen. Why not? Because net force equals 0. They cancel each other out. Everything's in equilibrium. And the final question says, based on your observations, what can you say about an object at rest pulled in opposite directions by unequal forces? That's when you're going to have a non-zero net force. Okay, so an example of this would be if somebody was pulling with a force of 5 newtons and another person would be pulling from the other direction or in the opposite direction with a force of 7 newtons. And now we're going to have an overall net force of 2 newtons to the right, and therefore we are going to have motion, we are going to have acceleration towards the right. So as long as the net force is not 0, as the net force is not 0, it will move. Okay, so just to recap today's lesson, forces are a push or a pull. Forces are measured in newtons, that's the unit for forces. If forces are balanced, then that's what we call a scenario of equilibrium. If all the forces acting on the object cancel each other out and they are in equilibrium, then we say that's a net 0 or net force of 0, and there will be no motion or no movement. The object will remain at rest as long as it's at rest to begin with. If the forces are unbalanced, which means there is a net force acting on the object, then the object will move towards the direction of the net force. Okay, that is all for now. What I would like to say is like, share, and I will see you ala khair. Take care. Bye bye.